Hello everyone, here are videos for civil engineering. Welcome to the channel Amazing Civil Engineering Studies. Here we have different videos on all topic of civil engineering. Please subscribe and press bell icon, like and share as many as possible. In this video we will learn about deep foundation and its types. Deep foundation. Deep foundation is a type of foundation that transfers building loads to the earth farther down from the surface than a shallow foundation does to a subsurface layer or a range of depths. Deep foundations carry building loads to more competent strata that are down too far below the ground level, preventing the surface conditions from affecting their base-bearing capacity. They usually go beyond 3 meters below the finished ground surface. Foundation selection criteria for buildings. 1. Loads of structure. Loading conditions coming from the structure is one of the factors that govern foundation selection. It is influenced by type of building, type of construction material, environmental factors, earthquake susceptibility. Selection of materials such as bricks, stone, steel, and concrete for construction affect the selection of foundation. Settlement calculation of foundation is another factor that associated with loads of the structure and affects foundation choice. In case of low-rise building, shallow foundation is preferred. However, for high-rise building, deep foundation is required. Deep foundation is provided because ground at greater depth are highly compacted. 2. Soil-bearing capacity. Soil-bearing capacity is one of the most crucial criteria that affect the selection of the appropriate type of foundation. Decision can be made to choose shallow or deep foundation based on the soil-bearing pressure. An allowable bearing pressure of at least 100 kN/m2 or higher is effective for shallow foundations up to 4 stories. However, higher structures can consider a raft foundation provided that the modulus of subgrade reaction shall not be exceeded when calculated. 3. Soil types. There are different types of soil like sandy soil, loose soil, clayey soil, and expansive soils. Form the surface to a depth of 3 ms termed as topsoil, and subsoil begins after 3 m depth. Characteristics specifically bearing capacity of both topsoil and subsoil layers would to a great extent controls the foundation selection. For low bearing capacity soil, stronger and suitable foundation shall be selected compared to with case where the soil has strength bearing capacity. The bearing capacity is the ability of soil to safely support structural loads without suffering shear failure and intolerable settlement. 3.1 Clay soil. Clay soil has great capacity for water retention, that is why great expansion and shrinkage are expected in this type of soil. As a result, foundation structure can suffer from great settlement and uplift pressure, that is why clay soil is not desirable. Applicable codes such as British Standard recommends minimum depth of 1 m for foundation and 3 m if there are trees around. Raft/mat foundation is the best foundation type to be built on clay soil, and ribs and beams can be incorporated into it to increase its stiffness. If raft foundation is costly, imposed loads are large, or strong soil layer is not available at shallow depth, then under-reamed pile should be selected. In clay soil, it is recommended to collect and drain rainwater, extend foundation to a depth where moisture fluctuation does not occur, remove weak and shallow soil layers such as black cotton soil, execute construction during dry season if possible, and distribute structural loads as uniform as possible. In the case where a shallow firm soil layer covers soft clay soil layer, it is advisable to use wide reinforced strip foundation. In this manner, the effect of loads on weak soil layer is reduced. Pile foundations are recommended for high-rise buildings and whenever uplift is expected. 3.2 Peat soil. It is considerably porous, easily compressible, and dark brown or black color soil which is commonly present near wetlands. It undergoes expansion and shrinkage due to moisture fluctuation, extremely weak in terms or load carrying capacity. So, it should be either removed. Strong strata and strip foundation is good option in this case. If the thickness of peat soil is great and its removal is not economical, then other foundation types should be selected. For instance, concrete piles extended to the firm soil layer below, pad and beam foundation took to firm strata below for small projects. Or raft foundation for the case where firm strata are not available at reasonable depth but there is hard surface crust with 3-4 m thick of suitable bearing capacity. 3.3 Silt. Siltous soil, which is smooth to touch, is generally not suitable for foundation structure because of its expansion which exert pressure against foundation and damage it. The silt retain moisture and does not drain water easily. Reinforced concrete spread and isolated pad footings are appropriate if silt or silta clay is stiff and extends to a great depth. The depth of the foundation should be greater than the zone of erosion and the zone of swelling and shrinkage. 3.4 Sand and gravel. Sand and gravel allow water drainage, that is why do not cause structural movement. Moist compaction of soil and sand make good support for foundation structure. Dry compact gravel, or gravel, and sand subsoils are adequate for spread and strip foundations. Generally, a depth of 700 mm is acceptable, as long as the ground has adequate bearing capacity. If gravel is submerged in water, the bearing capacity is declined by half. That is why it is important to keep the foundations as high as possible. A shallow, reinforced, wide strip foundation may be suitable. Sand holds together reasonably well when damp, compacted, and uniform, but trenches may collapse and so sheet piling is often used to retain the ground in trenches until the concrete is poured. If loose sand is extended for great depth, then it is recommended to compact it and use spread footing. Alternatively, raft, driven pile, augured pile, or cast-in-place pile can be selected without the use of compaction energy. 3.5 Rock. Generally, rocks such as limestone, bedrock, and sandstone have substantially high bearing capacities. This makes it suitable for supporting foundations of commercial and residential buildings. 3.6 Loam. Loam is the best option to support foundation because of its uniformly balanced characteristics. It maintains water at balanced rate and hence neither shrink or expand to an extent that damage foundations. Loam is a combination of clay, silt, and sand, and dark in color and soft, dry, and crumbly to the touch. Isolated footing is the most desired type of foundation for loam soil. The depth and area of foundation is dependent on bearing capacity, depth of groundwater table, and depth of load. 3.7 Previously used soil. If the site previously used for buildings such residential, mining, industrial, or other structures, then obstruction such as ground contamination can hinder immediate excavation works. Such considerations need to be taken into account while the type of foundation is selected. If for instance loose sand extends to a large depth, then raft foundation can be selected to evenly distribute the load, and pile foundation would be required for heavy structures such as multi-story buildings. 3.8 Mountain soils and forest soils. Mountain soils and forest soils are most likely to have boulders at various depths, so pile foundations are not suitable. For residential buildings with 1 or 2 floors, isolated reinforced pad foundations are suitable. For single-story buildings, reinforced concrete strip foundations are suitable. For ease of construction. The choice of foundation should be made keeping in mind the ease with which it can be constructed at the site. The construction of different types of foundation requires labor of different skill set and different level of skills. 5 Water table level. Water table is another significant criterion that affect the foundation selection. Foundation should not be placed on soil that undergo expansion and contraction due to water table fluctuation. So, it should be construction on fully dry soil or on fully wet soil. If the groundwater table is located below the formation level of the foundation, then a shallow footing like isolated or combined footing should be chosen. Moreover, for higher water table, raft mat footing should be proposed. This is to counteract uplift pressure and counter the effect caused by water to avoid any overturning moments at the early stage of construction. If this option cannot be executed, then deep foundations like micro-piles or board piles should be considered to provide the necessary uplift resistance. 6 Adjoining structure / water bodies / slopes. Adjoining structures, water bodies, slopes are parameters that need to be considered for selection of foundation types. When foundation of the neighboring structure is very close the foundation to be construction, it may influence the choice and the safety of the adjoining structure. If the foundations of an adjoining structure are very near to the target foundation, it may affect the choice as the safety of adjoining structure is of paramount importance. The selection of proper foundation type would be more challenging if the neighboring structure is high-rise building or an old property. Factors such as closeness to a river, lake, natural drain, or vicinity to a slope should be taken in counting. Isolated RCC pad foundations under stilts are usually preferred for buildings on sloping grounds. No residential buildings should be constructed on slopes steeper than 25 degrees. 7. Natural disaster and extreme weather. If the area has a history of severe natural events or extreme weather, then these parameters should be selected. Taken these parameters into considerations. The past record or data of natural disasters and extreme weather should be employed as a base for foundation selection. 8. Economic design. When there are number of feasible foundation choices for the given project site, economical factor may influence the selection of the foundation. Nonetheless, choosing an economical foundation should not compromise the safety, workmanship, strength, and durability of the foundation. Soil tests required for deep foundations. While the composition and depth of the bearing layer for shallow foundations may vary from one site to another, most pile foundations in ALOCLI encounter similar deposits. Since pile capacity based on soil parameters is not as reliable from load tests, as a first step it is essential to obtain full information on the type, size, length, and capacity of piles, including details of load settlement graph, generally adopted in the locality. Correlation of soil characteristics, from soil investigation reports, and corresponding load tests. From actual projects constructed, is essential to decide the type of soil tests to be performed and to make a reasonable recommendation for the type, size, length, and capacity of piles since most formulae are empirical. Soil tests. 1. Direct shear test. 2. Standard penetration test, SPT. 3. Static cone penetration test, CPT. 4. Vane shear test. 5. Undrained triaxial shear strength. 6. Pressure meter test. 7. Groundwater condition and permeability of soil. Generally, the following tests may be required to obtain certain required data. 1. Direct shear test. It is conducted to estimated effective friction angle of cohesion-less soil. Nonetheless, there are correlations which are developed to evaluate effective friction angle of cohesion-less soil. 2. Standard penetration test, SPT. It is performed to determine the cohesion, and consequently the adhesion, to determine the angle of friction, and consequently the angle of friction between soil and the pile and also the point of resistance, for each soil stratum of cohesion-less. Soil of soil. 3. Static cone penetration test, CPT. This test conducted to determine the cohesion, and subsequently the adhesion, for soft cohesive soils and to check with SPT result for fine to medium sands. Hence for strata encountering both cohesive and cohesion-less soils, both SPT and CPT tests are required. For Vane shear test. It is used to estimated undrained in situ shear strength of impervious clayey soils. 5. Undrained triaxial shear strength. It is carried out on undisturbed soil samples, obtained with thin-walled tube samplers, to determine cohesion and angle of internal friction for clayey soils. Procedures for conducting this test is provided by ASTM D2850-03, 2004. In case of driven piles proposed for stiff clays, it is necessary to check with the cohesion and angle of internal friction from remolded samples. Drained shear strength parameters are also determined to represent in situ condition of soil at end of construction phase. Details of this test procedure can be found in ASTM. 6. Pressure meter test. It is performed to determine the stress-strain curve of horizontal loading. The equipment is either inserted into pre-drilled borehole or a self-boring pressure meter is used. Unless the soil is isotropic, the same value cannot be adopted for the vertical direction. This test is performed specifically for piles that subjected to lateral loading. 7. Groundwater condition and permeability of soil. Groundwater condition and soil permeability influence the choice of pile type to be recommended. Hence the level at which water in the borehole remains are noted in the bore logs. Since permeability of clay is very low, it takes several days for water in the drill hole to rise up to groundwater table. Groundwater samples need to be tested to consider the possible chemical effects on concrete and the reinforcement. Result of the cone penetration test for the same soil show substantial scatter. Hence, they need to be checked with supplementary information from other exploration methods. Types of deep foundations. Common deep foundations include pile foundations, caissons, cylinders, basements, hollow box foundations, buoyancy rafts, shaft foundations, pile foundations. Pile foundations are constructed through driving preformed units into the required founding level or by drilling in, driving tubes filled with concrete to the desired depth. The tubes can be filled with concrete in different ways. They can be filled during or before withdrawal, or through drilling unlined, partly lined, or wholly lined boreholes before being filled with concrete. These foundations are used when the soil, constructional or economic conditions make it necessary to transmit loads of structures to strata that are beyond the reach of shallow foundations. Besides supporting structures, piles can be used to help resist uplift, overturning, and lateral forces. They are used as foundations for waterfront installations, bridges, and buildings. Types of pile foundation. Depending upon the above-mentioned factors, piles are generally categorized into following three types. End-bearing piles, friction-bearing piles, combination of end-bearing and friction-bearing piles. These has been discussed below. 1. End-bearing pile foundation. End-bearing piles, also called as point-bearing piles, are selected when the depth of hard soil strata or bedrock at site is within reasonable depth. The length of pile to be used can be easily computed based on bedrock depth obtained from soil exploration borehole records. In this case, the loads from structures are directly transferred the hard soil through bearing action of pile bottom tip, and it does not require the use of skin friction to resist loads. The cost of construction of piles in such cases is optimum. The ultimate capacity of pile or pile group depends on the bearing capacity of bedrock or hard strata. Number of piles to be used in this case depends on the loads from structure and individual capacity of piles. In this case, Q U equals Q P, where Q U is the ultimate load capacity of pile foundation. Q P is the load carried by the end-bearing pile or pile group. In case when the hard bedrock is not available at reasonable depth and fairly compacted hard strata of soil exists, then piles should be extended a few meters into the hard soil strata. 2. Friction pile foundation. Friction piles resist the loads from structures due its skin friction with soil. This type of pile foundation is selected when a hard stratum is available at large depth and construction of end-bearing pile becomes uneconomical. Then number of piles in a group is selected to resist the load from structure through its skin friction. This type of pile foundation also resists loads due to end bearing, but its value is small, thus it is neglected in calculation. In this case, Q U equals Q S, where Q U is the ultimate load capacity of pile foundation. Q S is the load carried by the friction pile or pile group. The load is transferred to the soil through friction in case of sandy soil and adhesion in case of clayey soil. Loose sand and soft clays may not provide sufficient skin friction or adhesion resistance to heavy loads from structures. Combined end-bearing and friction pile foundation. This type of pile foundation is mostly used in construction. The advantage of using this pile is that it can resist loads from structures through both end-bearing and friction resistance. This pile has high pile capacity and is economical. This pile is used when the soil exploration results shows hard bedrock or fairly compacted soils at reasonable depth and soil above bedrock supports skin friction resistance. In this case, Q U equals Q S plus Q P where Q U is the ultimate load capacity of pile foundation. Q S is the load carried by the friction pile or pile group. Q P is the load carried by the end-bearing pile or pile group. The load is transferred to the soil through friction in case of sandy soil and adhesion in case of clayey soil. Caissons. These are hollow substructures that can be constructed near or on the ground surface and are sunk to the desired level as a single unit. They have an enormous load carrying capacity and are commonly used for bridges. What is a caisson foundation? A caisson foundation, also called as pier foundation, is a watertight retaining structure used as a bridge pier, in the construction of a concrete dam, or for the repair of ships. It is a prefabricated hollow box or cylinder sunk into the ground to some desired depth and then filled with concrete, thus forming a foundation. Caisson foundation is most often used in the construction of bridge piers and other structures that require foundation beneath rivers and other bodies of water. This is because caissons can be floated to the job site and sunk into place. Caisson foundations are similar in form to pile foundations, but are installed using a different method. It is used when soil of adequate bearing strength is found below surface layers of weak materials such as fill or peat. It is a form of deep foundation which are constructed above ground level, then sunk to the required level by excavating or dredging material from within the caisson. Caissons, also sometimes called piers, are created by augering a deep hole into the ground, and then filling it with concrete. Steel reinforcement is sometimes utilized for a Caissons are drilled either to bedrock, called rock caissons, or deep into the underlying soil strata if a geotechnical engineer finds the soil suitable to carry the building load. When caissons rest on soil, they are generally belled at the bottom to spread the load over a wider area. Special drilling bits are used to remove the soil for these belled caissons. The caisson foundations carry the building loads at their lower ends, which are often bell-shaped. Functions of caisson foundation. The foundation system of and the soils beneath the building prevent the complex from moving vertically. When a load is placed on soil, most soils settle. This creates a problem when the building settles but the utilities do not. Even more critical than settlement is differential settlement. This occurs when parts of your building settle at different rates, resulting in cracks, some of which may affect the structural integrity of the building. Conversely, in some rare instances soils may swell, pushing your building upwards and resulting in similar problems. Therefore, the foundation system must work in tandem with the soils to support the building. Types of caisson foundations. Box caissons, excavated caissons, floating caissons, open caissons, pneumatic caissons, sheeted caissons, Box caissons are watertight boxes that are constructed of heavy timbers and open at the top. They are generally floated to the appropriate location and then sunk into place with a masonry pier within it. Excavated caissons are just as the name suggests, caissons that are placed within an excavated site. These are usually cylindrical in shape and then backfilled with concrete. Floating caissons are also known as floating docks and are prefabricated boxes that have cylindrical cavities. Open caissons are small cofferdams that are placed and then pumped dry and filled with concrete. These are generally used in the formation of a pier. Pneumatic caissons are large watertight boxes or cylinders that are mainly used for underwater construction. Box caisson. This type of caisson is similar to open caisson except that it is closed at bottom. The caisson is cast and cured on land, and when required, it is launched in water and towed to the site for sinking. The caisson is sunk by filling sand, gravel, or concrete in the empty space inside. The place where the caisson base is to rest must be leveled, and as such box caissons are used in places where the strata of sufficient bearing capacity is available near the ground. In normal practice, the soft natural bottom soil of the river bed is dredged out to some depth and the trench thus formed is filled with sand to have a leveled base. The function of the sand layer is to uniformly distribute the superimposed loads over the soil below and thus avoid tilting of the caisson. Advantages and disadvantages of caissons. Advantages of caissons. Economics. Minimizes pile cap needs. Slightly less noise and reduced vibrations. Easily adaptable to varying site conditions. High axial and lateral loading capacity. Disadvantages of caissons. Extremely sensitive to construction procedures. Not good for contaminated sites. Lack of construction expertise. Drilled pier foundations. A drilled pier is a deep foundation system that is constructed by placing fresh concrete and reinforcing steel into a drilled shaft. The shaft is constructed by rotary methods using either a self-contained drill unit or a crane-mounted drill unit. The hole is advanced through soil or rock to the desired bearing stratum. Temporary or permanent steel casings may be used to maintain the sides of the drilled excavation if caving soils or water infiltration becomes a problem. Drilled shafts can be used to sustain high axial and lateral loads. Typical shaft diameters range from 18 to 144 inches. Drilled shafts, also called caissons, drilled piers, or board piles, have proven to be a cost-effective, excellent performing, deep foundation system that is utilized worldwide. Typically they are used for bridges and large structures, where large loads and lateral resistance are major factors. Construction of drilled piers. The construction of drilled piers involves the following three stages. Excavation of piers. Providing supports. Concreting. 1. Excavation of piers. Generally, auger drill is used for the excavation of drilled pier. Other drilling equipment, like rotary systems, hydraulic power etc., are also used as per the need. An auger is attached to a shaft and rotated under pressure to dig into the soil. When it is filled with soil, it is raised above the ground and emptied. See figure. When the soil stratum does not have the adequate bearing capacity, belled piers are generally used. For the formation of a bell, the auger is replaced by an under-reaming tool which consists of a cylinder with cutting blades that are hinged at the top. The cutting blades are in the folded position when the under-reamer is lowered into the hole. On reaching the bottom of the hole, the blades are spread outward by a mechanism. As the under-reamer is rotated, a bell is formed and the loose soil falls inside the cylinder, which is raised and emptied. The process is repeated until the bell is completely formed. The diameter of the bell is kept 2 to 3 times the diameter of the shaft. The angle of the bell is 300 to 450 with the vertical. The above-mentioned method of drilling is convenient for hard clays where the hole can be left open for a few hours without any support. In cohesionless soils below the water table, the hole is prevented from collapsing by providing a casing or by drilling in a slurry. When rock is encountered during drilling, special machines are required. 2. Providing supports to piers. There are 2 methods available for providing supports. Chicago Method, Gow Method. Chicago Method. In this method, a circular hole is excavated up to the depth at which the soil will stand unsupported, about 0.5 m for soft clay and 2 m for stiff clay. Vertical boards known as laggings are then set in position around the excavated face and are held tightly against the soil by steel rings. The shaft is then excavated further for 1 to 2 m and another setting of boards and rings is made. The process is repeated until the desired level is reached. The base of the shaft is then belled out. Gow Method. In this method, excavation of the hole is done manually. Telescopic steel shells are used to support the soil and are extended as the hole is deepened. The shells are removed as the concreting progress. One section of the shell is removed at one time. The minimum diameter of the hole in this method is about 1.25 m. 3. Concreting of piers. 1. After the hole has been drilled to the required depth, the shaft is dewatered and the bottom is cleaned. The casing, if used, is removed. 2. The reinforcement cage is then inserted and concreting is done. As far as possible, concreting should be done in a dry shaft hole. 3. Concreting can be done in a dry hole by gravity pouring, provided the concrete does not strike the sides. However, if dewatering is not possible or slurry is used to support the shaft sides, concrete is placed using a tremie. See figure. Figure showing concrete is placed using a tremie. Advantages and disadvantages of drilled piers. Advantages. Disadvantages. A single drilled pier can take up the load of a group of piles. Concreting requires stricter supervision. The quality of concrete obtained is generally inferior to that in precast piles. They have higher resistance to lateral loads. Deep excavation of drilled pier, if not properly supported, can cause substantial subsidence and damage to adjoining structures. Compared to pile driving, equipment needed for drilled pier is lighter and there is no noise during construction. Load tests are difficult in case of drilled piers. Ground heaving does not exist in the case of drilled piers. More subsurface investigations are required in case of drilled piers. Inspection of the base and sides of the pier is easier. Base of drilled pier provides greater bearing capacity and great resistance to uplift. They can be used even when the soil contains boulders. Concrete caissons. 10 or 12 diameter holes are drilled into the earth and embedded into bedrock 3 to 4 feet. Usually used for the structural support for a type of foundation wall, porch, patio, monopost, or other structure. 2 or more sticks of reinforcing bars, rebar, are inserted into and run the full length of the hole, and then concrete is poured into the caisson hole. A caisson is designed to rest on an underlying stratum of rock or satisfactory soil and is used when unsatisfactory soil exists. Caisson construction process. After some initial form work and concrete pours, the cutting edge is floated to the breakwater by towboat and fastened to the caisson guide. Concrete is placed, poured, into steel forms built up along the perimeter of the box. With every concrete placement, the box becomes heavier and sinks into the water along the caisson guide. Forms are also built inside the box around the air domes and concrete is placed in between. The resulting open tubes above the air domes are called dredge wells. When the caisson finally touches the river bottom, the air domes are removed and earth is excavated through the long dredge well tubes. See figures. The caisson sinks into the river bottom. Excavation continues until the caisson sinks to its predetermined depth. As a final step, concrete is placed, poured, into the bottom 30 feet of the hollow dredge wells and the tops are sealed. Straight shaft drilled piers, caissons. Used in moderate to high swelling soils. This is one of the most effective foundation designs for use in sites that contain expansive soils. Purpose is to attain required penetration into zone where there is little or no seasonal moisture variation. Current standard of care in the area is a minimum penetration of 6 feet into bedrock and minimum length of 16 feet. Dead loads should be as high as practical. This design requires relatively long spans between piers and more reinforcing in grade beam. Caissons into bedrock. Friction piers into stiff clays. End-bearing beld piers. Appropriate voiding should be constructed with void material of appropriate strength and thickness. Fig. A series of 1.2 meter thick diaphragm wall panels were joined to form a 24 meter diameter caisson shaft. 4 of these caissons were built to provide a sound base for the foundation of the main structure of the building tower. The photo shows the excavation work using typical excavating machines inside one of the caisson shafts. Construction process. Following steps could be followed to build a caisson. We must set the place first for the establishment of the caisson. Then the first 3.7 MOF caisson is precasted. Next, with the help of towboat, the caisson is floated to its location by and tie it to the caisson guide. After that, concrete is poured using slip forming, and as concrete goes, the box becomes heavier and sinks into the water along with the caisson guide. Mooring cables are used to hold the caissons in place. When the caisson finally touches the river bottom, the mooring cables are removed. Finally, the cap is poured. Cylinders. These are small caissons with only a single cell. Cylinder is sunk into the ground to a specified depth by augering a deep hole into the strata. The cylinder is then backfilled with concrete, thus creating the foundation. Basement foundations. These hollow substructures provide storage or working space below the ground level. They're constructed in open excavations. The functional requirements govern their structural design. Buoyancy rafts. Buoyancy rafts, also known as hollow box foundations, are designed to create a semi-buoyant or buoyant substructure below which the loading on the soil is decreased to the required low intensity. They can be constructed in open excavations or sunk like caissons. Buoyancy rafts are more expensive than traditional forms of foundations. For that reason, their use is usually restricted to sites that are on silts, soft sands and other alluvial deposits that are very deep, or where loads can be kept concentric. Schemes requiring underground tanks or where it's economical to incorporate deep basements into the design are common. Shaft foundations. These foundations are constructed by drilling a cylindrical hole within a deep excavation and subsequently placing concrete or another prefabricated load-bearing unit in it. Their length and size can be easily tailored. Drilled shafts can be constructed near existing structures and under low overhead conditions, making them suitable for use in numerous seismic retrofit projects. It may, however, be difficult to install them under certain conditions such as soils with boulders, soft soil, loose sand, and sand under water. Methods of excavation used for deep foundation construction. Excavation methods for deep foundation construction. Full open cut method. Bracing excavation method. Anchored excavation methods. Island excavation methods. Zoned excavation methods. Top-down excavation methods. Full open cut method. It divided into two major types including sloped full open cut as shown in figure. Cantilever full open cut as illustrated in figure. The former is assumed to be economical since the site of excavation would be sloped and does not need any support to hold foundation wall. However, if the slope is considerably gentle or the excavation is largely deep, it will costly. The latter needs retaining wall to support foundation wall soil and prevent collapse of foundation wall, but it neither require backing nor slopes. Therefore, it cannot categorically be claimed that which method is more cost-effective. The economical method may be distinguished based on analysis, design, and evaluation results. Bracing excavation method. Bracing excavation as shown in figure is the placement of horizontal struts in front of retaining wall to hold excavation wall material pressure. Bracing system consists of wale, strut, center posts, end braces, and corner braces. Earth pressure transfer to horizontal struts through wale, and the purpose of corner and end braces is to reduce wale span without increasing strut number. Center posts prevent the failure of struts due to their own weight. Anchored excavation methods. In this technique, anchors as shown in figure are installed to counteract against earth pressure. Configuration and components of anchored excavation technique are illustrated in figure. Bonded portion of the anchor provides anchoring force that works against earth pressure, whereas unbonded part of the anchored transfer pressure to the anchor head. Anchor head transfer loads to the retaining wall. The anchoring force is greatly based on the soil strength. The higher the soil strength, the greater the anchoring forces. This technique is not suitable for clay and granular soil with high groundwater table. Lastly, it requires short time to complete excavation with great efficiency and suitable for large areas and shallow depth. Island excavation methods. In this method, the center of excavation area is dug and excavated material placed close to the retaining wall to create a slope. After that, the major part of the structure would be constructed at the center of the excavation. Then, the sloped soil will be excavated and struts will be placed between retaining wall and the main structure. Finally, the struts will be removed and remaining parts of the structure will be constructed. Sometimes, it might be required to use anchored or braced technique to remove sloped soil material, specifically when they zoned excavation methods. Diaphragm walls are used as a retaining wall in the zoned excavation method. Deformation of the longer span wall would greater than short span wall as explained figure. So, the deflections of longer span walls are declined by dividing excavation area into small area to decrease wall deformation and settlement as shown in figure. The excavation will begin in area B while area A would be left to support the wall of area B. Then struts in area B would be installed and excavation starts in area A. This process will continue in stages till the whole excavation is completed. it can be clearly observed that the load on diaphragm wall would be considerably large and hence deflection would grate if the area had not been divided into smaller area. In this method, construction begins from the top to the bottom of excavation and superstructure construction starts after the construction of the first slab is completed. So, slabs are constructed after each stage of excavation is finished. The slabs play the same role as struts in holding earth pressure. Construction process order include retaining wall construction, pile construction under column of superstructure, placing columns on piles, and installing formwork for the first slab at the top. Then other slabs of the wood be constructed after each excavation. This technique would need short construction time, but the cost is higher compared to other methods. Another advantage is that construction area safer since slabs are stronger than struts. Figure showing top-down construction. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.